Hello and welcome to Predictive Modeling with R. My name is Brian Cafferkey, and you can see the link at the bottom of the slide. If you go to github.com/bcafferkey/shared, you'll find all my content on YouTube. This one is under the folder R Predictive Modeling. Also, it's kind of a screenshot to show you that I have many videos on YouTube, so please subscribe, let people know about them. You know, I really like to maximize value, that people get things out of it. I've gotten some amazing comments from people, which I appreciate. And, you know, give me feedback. Hopefully you like what I'm doing, and always like to hear from people. So I do have to warn people, this content is rated R for strong language and graphics. So if you're offended by such things, you may want to leave now. So where are we heading? We're going to briefly talk about the R language, and I mean very briefly. I did do an intro to R, and I have an entire series, paid series on Pragmatic Works, where they do I did a whole introduction to the R language in 92 modules. This is going to be just enough so that you can make some sense of the code if you haven't seen R before. We will discuss what a predictive model is, and I do want to point out that whether you're using R, Python, SAS, or any other language, the concepts apply, so it really doesn't matter, but we'll talk about that. We'll walk through training a predictive model, and we'll discuss how to evaluate if the model is actually working well, because obviously if you train a model and you're ready to start using it to find out, predict new instances of things happening, you want to make sure it's working well. And I'm going to kind of tie in some cautions and recommendations, things that I've had a lot of people ask me, customers and etc., ask me questions. So I work for Microsoft as a data solutions enabler, and I've worked in consulting for years and many things. And so over the years, I've gotten certain questions and things, and I do want to make sure I caution a little bit as well, but not a good thing. First thing I want to say is have fun with this. We're in a great age. We've got cloud, we've got AI, we've got machine learning, and it's all like new shiny toys, right? If you got into this field of programming like I did because you liked it, that was cool, and you think, and I'm so excited about it, I even record things like this on weekends to tell other people how cool it is. Have fun with it. This slide, I particularly put the picture of a toy that I got when I was a kid, this Lost in Space robot, and it has lots of bells and whistles and lights and everything. But I love this thing, and the thing was that even though it was a bit complex to learn how to use it, I didn't think about that. I just thought about how cool it was and how fun it was. And I want to encourage you, when you get into data science, machine learning, to do the same. Have fun. It's cool. You can use it whether you're doing fantasy football, trying to predict the horses, or just trying to win at the slots. There's probably something for everyone in here, or hopefully in your job as well. All right, so I'm going to start with R, and I really like R as a language. I also like Python, and I want to say that to start with, R is an open source language for data science. That's the easiest way to start. And when would you use R? Well, the thing to understand is R is really geared towards statistics, which is why it's such a great language for predictive modeling and machine learning. It has amazing libraries built into it, and you can add on to it to do visualizations. So if you think of something like Power BI, which does all these awesome visualizations, using the R language, you can do a lot of similar types of things. Of course, Power BI is designed to be drag and drop and visual. With R, you do a little coding, but you can get some really amazing stuff. Also analysis, so it's really designed as a language to let you drill down and look into your data and see what you can tell from your data. What's the data? What's the story that your data is trying to tell you? And again, related to that is exploration. Explore the data. One of the things I really like to highlight there is sometimes the real value is in the exploration itself. You think about climbing Mount Everest, like yeah, you get to the top, but what about the journey getting there? And sometimes you find there's things in your data you didn't know. For instance, without even getting to predictive modeling, you may see patterns and you start to realize, like, wow, my store's sales go up at certain times of day. Why is that? Without even predictive modeling, mind you. And then you realize there's a store next to you. Maybe it's like a gym or a fitness center, and you're running a coffee shop, and you realize, wow, everybody goes into the gym, and when they're coming out, they buy coffee and donuts or something. And then at the end of the day, you get the same thing all over again. So you may see that there's stuff your data is telling you were never really looking at that could be helping you understand perhaps you've got a dependency on other businesses around you that affect your sales. And that's important because you decide you move your business, you're no longer near the gym, it could hurt your sales. Or maybe you can find other correlations. So finding insights in the data is really important, and I think sometimes that can be the real gem. You know, we have, besides coming up with Tang, the U.S. involvement in space and all that, and sending rockets into space, really brought us into the computer age. So the outcome became massive stuff there. Some features of R: it's a scripting language, which means you can type in at a console, one line at a command, almost like DOS or in PowerShell or Bash or Python, but you can also store programs and scripts and execute them. Has a vast library of statistical functions, built-in support to create, as I mentioned, visualizations, but most importantly, there's extensive free open source libraries that were developed by the user community or developers in the user community, and these can get into very specialized areas. So if you're looking at genomics or bioinformatics or different things, that's my area. I tend to focus on healthcare, but also in finance and things. You'll find lots of libraries, and they often give you data with it, so you can play with it and really explore right there without having to, try to find data sets to use. And so you can just download a lot of these. There's thousands of them, and that's one of the things that makes R such a great language. And there is support for object-oriented programming. Python, you tend to always see object-oriented programming. It's kind of inherent in the language, though it doesn't require it. Kind of lends itself very strongly that way. With R, you don't tend to see it as much, but it does support it. Now, to get R, if you want to run these demos, you always have to get the R language, and it can be a little confusing. Sometimes people think they can just get RStudio, and that gives them the language, but it actually doesn't. The R language is maintained by the Comprehensive R Archive Network, better known as CRAN, and the first link in here above, you can go to CRAN, download R for your version. It runs on, you can get Windows version or Linux or Macintosh, whatever, and then you want to install your IDE. Now you can use R directly with that. There's a simple editor in there, but RStudio is by far the most popular interactive development environment for R. Really powerful. We're going to use it, and yeah, so let's get in there. And I'm just showing you here the slide once you've installed RStudio how you get in. And when I go in to do my demo, you're going to see this screen, which is the RStudio screen, and there's ways of configuring and arranging how you want, but things to call out is the upper left hand corner is going to be where all the scripts are, and you can have multiple scripts open at once for the tabs. The console at the bottom, I could type in commands directly, or if I run scripts in the window, the commands will actually show up, or the output will show up in the console window, not unlike Python. On the right hand side, you can see I have an environment area. So if I create things in memory, I can go in and see what I've created, which is a really nice feature. And I have a history window, which will show me all the commands I've entered, all the different commands I've run. And I have a tabs below here. I can navigate and open files with the Files tabs. You're seeing the Plots tab displayed, which is the graphics I'm doing. You can find R packages, which is libraries of additional R functions. And I can navigate that way. So again, it's a really rich environment. I'm going to touch very quickly on the R language before I jump in. So just a few things if you haven't done R. Again, if you don't know R at all, it's probably good to go do some research on R. You will not need to know R really to get benefit out of this video, but it's an awesome language and worth learning. First thing is R is case sensitive. So a lowercase a is different than an uppercase a, say in a variable name, as the script shows. The other thing you'll notice is that instead of an equal sign, usually people use a left caret and a dash. Now is it required? No. But you won't look cool if you try to code R using equal signs for assignment. It's just not the conventions in R, so when in Rome, do as the Romans, and I think following that convention is the best advice. You'll also notice that generally it's a very function-based language. Although I mentioned you can do classes and objects, most people seem to code around the functions. So you'll see the print statement, and functions typically have the name of the function and then parentheses, and then the variable parameters you're going to pass into it. So you can see print and then parentheses a. That print is a function and it's going to print out a. The value, whatever is in there. Cat is function. You'll also notice there's these braces to mark beginning and ends of blocks of code. So if you've done C#, things like that, you've probably seen that same exact convention. I find R very similar in sort of structure and the look and feel of it to stored procedure coding in like SQL Server, which is probably why I really like R, because it's very function based. It's very simple, and it uses similar conventions, and yeah, that's about it. The only other thing I'll mention here is that the pound sign is used to put comments in your code, and that's about it. And we will talk about, we're going to use an object, which is how we train models, called a data frame. And a data frame is really just like an in-memory table. So if you used Excel and you just had one Excel spreadsheet up, you might sort and everything else. That's kind of like an in-memory table. If you use SQL Server and you do queries, you know, you bring a table in, you sort it, etc. The biggest difference here is you bring data in and it's sort of in memory and you can sort and do things with it. So it's ideally designed when you're using, you know, on your client machine doing code with data frames, that they're not too big because you're going to fill memory up if you get to like too large a data frame. So this slide shows a pretty good example, I think, of loading a data frame. There's many ways to create data frames in R, but one is using this read.csv function. And you can see here it's pointing to a CSV file, and it says header equal t, meaning true. So it's going to use the header at the top of the file to get the column names. So typical CSV files, you have what are the names of columns. CSV files are typically separated by commas because they stand for comma separated, the CS. And you can see, and also it tells you the SEP comma says it is a comma. So even though you read CSV, you could have other separators if you just identify what the separator is. Once I've done that, R automatically returns that file in what's called a data frame, and you can see the next line, you type in sales data and it just displays some of the rows of the data frame. And then the class statement, and this is basically stuff as if it was typed in the console. The class statement tells you what type of object you have. So when you say sales data, it tells you it's a data.frame. So that's how you know. We'll see more of this, but I just want to give you a smattering. So now we're going to get into the crux of our presentation, which is machine learning and specifically predictive modeling with R. So what is predictive analytics or predictive modeling? It attempts to determine an unknown variable based on known variables. So it's doing probability calculations. So you're using history to predict the future. I'm going to use, for instance, sales history. What have I typically made in the past to predict what do I think future sales will be? And you can imagine a lot of variables could go into trying to determine that. What is the inflation index? What do interest rates look like? How is the economy doing? You know, what time of year is it? If you're in something like, we'll say, sell pools, I'm guessing swimming pools don't sell as well in the winter unless you happen to be located in the south. And so even geography can play a big factor in all these things. So the idea, though, is with predictive analytics is you're trying to use past information to predict a future variable, a future thing. And it's a specific thing, like what do I think future sales will be? Do I think this person will get diabetes or will they not? You know, things like that. So that's the idea behind it. So again, a predictive model is determining the probability, the probable value. We don't know. Now, machine learning will not give you a guaranteed this is absolutely going to happen thing. It's doing more probabilities. It's highly likely, hopefully, if you get a good model. So for examples, and what it does to do that is you find other variables that have a relationship to the one that you want to predict. So for instance, we can see there's a strong relationship between the gross sales a company makes and profit. The more we sell, right, the more likely we're going to make more money. Now, of course, if we're selling at lower than it costs us to make it, then we have an inverse relationship. We're going to actually lose money as we sell more. But hopefully, you're running a business well, and you know to make sure your costs of production are lower than what you sell things for. So gross sales is likely to go up as profit goes up. And we can see this diagram here showing that kind of relationship. That's called a linear relationship. As one thing climbs up, the other goes up. As one value goes up. So for instance, I'll show you in a minute, for instance, foot size to height. Generally, the bigger your feet, the taller you are. There's those kinds of relationships. So here we can see that as sales is increasing, then also the profit's going up. But it's not necessarily one-for-one because taxes, other things, costs that may vary can affect whether or not it's a one-for-one. So for every dollar increase in sales, we don't necessarily get a dollar increase in profit, but we will get something hopefully. So you can see in this diagram, the actual dots would be actual sales and profit at each point, the intersection. So here's sales and profit. And notice there's this line going through. So you would first plot this without the line, and then you're going to try to fit the line into the diagram, the chart, and you want to get this sort of average through. That's what you're really doing in the linear regression type of model. You're calculating the average through points so that when you predict something, you're not going to get the actual at any point in time normally. You're going to be getting some sort of an average. So you're going to be a little bit off. The distance between where the actual dots fall and that line is your error. So that's where you're going to be off, and that's called the error rate. So you need to consider those in your predictive modeling. How far off are you? Something I'm also going to talk about a little bit later is how widely varied. Can you imagine if these dots were really far off and all over the place, but I'm still trying to draw a line through it? That variance is going to affect how really good the predictions are as well. If it's very, a lot of variance in the numbers, it could be difficult to get really good predictions that are meaningful. Other linear relationship, we mentioned foot size to height, but also something like, say, study time to grades. Other factors will definitely go in, but generally speaking, you would expect that the more time someone spends, spend studying, more likely they'll get better grades. The distance to travel time is another one. If the further I am for something, if I'm going from LA to Boston, I can expect that's going to take a while. However, there are other factors that also play into it. Time of day, etc., the traffic levels. But distance to travel time has some level of relationship, right? Now, when we calculate this relationship, this correlation, we do it as a representative number between 0 and 1. 1 represents 100% correlation, 0 is no correlation. So the idea here is if I were to walk from one side of the room to the other, for every foot I walk from one side of the room, I'm a foot closer to the other. That's 100% negative correlation because one's increasing while the other's decreasing. If I had something like foot size to height, I'm going to have generally a positive correlation. The bigger the foot, the more height. But it won't be perfect. It might be like 0.8 increase. So for every certain size, say shoe size I go up, maybe I go up 2 inches or 0.6 inches or something like that. So it's not a 1-for-1. So that's really important. But that correlation is really important. And again, it's a linear correlation. So let's take a moment. Let's stop and consider a simple example, and I want to try to draw out like that this is not something really new. We've done this since the beginning of time, I think, and so it's not really mysterious. We're just bringing new tools to bear. We're using statistics, we're adding computing power, and we're adding some complexity to something we've been doing for a long time. So in my case, I like to consider, and I often do have to consider this because I work out of the Boston office, how long will it take me to drive into Boston on a given day? Well, what would I consider in that? Well, let's think about this. What would I have to consider? I want to know how long it takes to get into Boston. Well, without even doing any, actual data, I don't have to look back. I can use my own history of driving in, my own inferences. And what I know is the day of the week is probably one of the biggest factors. So on a holiday, probably not so bad, or I should say, on Monday, Tuesday, weekdays, it's going to probably be pretty difficult to get in if you're depending on time of day. So the time of day also factors in. So typically, if you're trying to go in during rush hour, 8 o'clock on a weekday, most days you're going to have trouble because you're going to take a while, and so the traffic will become a huge factor. But if it's a holiday, maybe not. That may be that because it's a holiday, there won't be any trouble at all. But even here, you have to be careful because Boston has a lot of stuff going on, say, on 4th of July. So it could be very difficult to drive into Boston on the 4th of July. What time of year is it? Another factor. If it's during like summer vacation periods, when July typically, traffic can be pretty low during the holidays in the winter. Also, a couple of weeks in there, it's really, really easy to drive in and out. One of my favorite times when I have to go in, that's when I like to do it. And also, where are you starting from? So I live about 40 miles outside of Boston, so I have to factor that in because even with no traffic or anything, there's a certain amount of time it's going to take, so that has to be factored in as well. And finally, once we do this, I can get a pretty good estimate, and I think you do too. Maybe there's a big city near you, something where you do have to think about when you're going and when you're not. I'm sure LA, New York City are places like that too. But you can be wrong, right? Sometimes I'm surprised. Usually I find when I go into Boston, I'm surprised more on the negative side because I'll be going in and it's noontime and maybe a weekday, and I still hit traffic. And I'm surprised, and I end up taking 3 times as long as I would have expected if there were no traffic. So traffic is the big factor. So the thing is, we can be wrong. And now that we know we can be wrong, we want to constrain that, right? We want to know how much could we be wrong? How likely are we to be wrong? And by how much? So that's kind of where we get into evaluating the model. So what are the uses of predictive models? We've probably seen a lot of them. We see them probably a lot nowadays. But one is classifying something. We actually implicitly get the benefit of predictive modeling with our email. So if you use like Hotmail or Outlook from Microsoft, they have a spam filter. And the spam filter, a good mail, by the way, is called ham. So if you didn't know that, take away. But spam or ham. So there's a filter in there, and so there's a model evaluating based on words in the email and things like that. It will say, this is very likely to be spam. So I'll put it in the spam folder. So that's something we use all the time. What group does something belong to? I saw a presentation in which Microsoft demonstrated, for instance, astronomers predicting based on the properties of an object in celestial space, out in space, what it was and whether it's a star or not, and then classifying the type of star or object automatically. So imagine it was able to do this for millions of different objects. You can imagine how long that would take for astronomers to individually go through and do that manually. So it was able to do that for them automatically and get a pretty good accuracy rate. Might be in a similar way, you might use something like take pictures of plants, and then by using analysis of the images, you could predict what species of plant it is, or specifically what plant it is. Will a person contract an illness? So I'm in healthcare, so that's a big one. Risk analysis of patients. Basically, how likely is a patient to get infections and surgery? What's the likelihood of contracting diabetes based on different factors, etc. And we're going to use a sort of healthcare case to do the demo. Will the patient be readmitted is a big issue in healthcare because readmissions are costly and bad for everybody. And in general, is a person at high risk. So what are the steps to creating a predictive model? So again, we're trying to create a predictive model, kind of to back up for a minute, is basically a simplified statistical program or a statistical program that will take input and predict an outcome. So we'll bring in something, for instance, like a new applicant for a loan, and based on probabilities, etc., looking at the data around that application, can we predict whether they're going to go into default or not, whether they can afford the loan or will they default on it, etc., or maybe transactions coming in trying to buy something on a website. What's the probability this is fraudulent? So those are examples of how we use predictive model. And so we call this little program and say, is this yes or no? What's the value predict? Give me a result back. So based on the input columns or features they call it, it'll give us an answer. So we'll see a better example of that in a minute, but I want to give you a sense like what do we mean by predictive model. So first thing we need to do to create a model is to analyze and clean the data. And by the way, there's the idea we need to train a model, so we prepare, that's creating the actual predictive model. But once we have it created, then we can just put it into use and use it with new instances of things coming in. So first step is analyze, clean the data. Determine the columns that you think will predict the answer, that can be effective in helping to predict an answer. Select a model to use. Train the model. Evaluate the model's effectiveness. And put the model into use. Pretty straightforward. We'll see there's different pieces, and I'm going to come back to some of this later to give a little more discussion. So this slide is meant to show you the overall steps, and it's a bit of a lot to take in, but I do want to kind of walk through it. It's not as complicated as you might think, but the key takeaways here is typically you get input data, and imagine we have, say, 1 million rows of applicants who have applied for loans, but it's historical, and we can see who has paid off the loans or not, for instance. So the typical thing we want to do is split the data off to training data, and that'll be the bulk of the data. In this case, about 80% we're going to use. And we'll take that training data, we'll put it through a model training program. And what that model training program is essentially going to do is we're going to tell it what columns we want to use, like maybe the income of the person, where they live, stability of employment, how long they've been employed, etc. Using those features, we're going to go through the algorithm, and it's going to create a statistical relationship basically between all these columns and predicting the outcome of yes, they will repay or no, they won't. So it's creating a little statistical program, and it's based on that training data we give it. So it's actually looking, it knows the answer, and it's sort of backing into the statistical relationship between that answer and all the input values. When it's done, it creates the predictive model. This is our program. It's going to be used to predict new instances of applicants where we don't know the outcome and we want to try to predict it. So we put that into a predictive model, and then we took aside, remember we pulled out, we didn't give it everything, we took about 20% or so, and we call that scoring data or test data. What we want to do is we're going to sort of like put that in our back pocket. We're going to use it as if it's new data. We're not going to give the answers this time to the predictive model, and we're going to actually let it predict an answer. What we can do by doing that is we've got the real answers here. We've now got predicted answers that outcome from the model, and now we can compare it. How good did it do? Was it 100%? Was it 50%? So you can see that we have that section, the split data, and that scoring data now goes into the predictive model to output predicted answers. And then we take the scoring data true answers, compare that to predicted answers, and we say, was it right or not? We get our percentage correct. Now, there's different ways to evaluate the scoring model. We're going to take a very simple approach to just get the concept across, but there are other ways of evaluating, and some of the ways we evaluate the outcome depend on the type of model and the type of variable we're predicting. But that's the basic gist of how this works. Now, the example we're going to use is something that's an R package, gives us everything we need, which is what I like, and it's called the birth weight data set. And the idea here is that we want to predict the likelihood that there will be a low birth weight baby based on the expected mother's characteristics. So we'll have the mother's age, the weight in pounds at the last menstrual period, the race, smoking, etc., all these variables. Now, we also have an indicator, which we're going to tell the model. This indicator is the birth weight. Is it less than 2.5 kilograms? So it's going to be in our data. That's how we're able to train it. We're actually going to end up pulling out the birth weight in grams because that becomes sort of redundant with the low or not birth weight, because the birth weight itself does tell us if it's low birth weight. So we can't use that in the actual prediction because that would be kind of silly. But again, the idea is we're going to have an expectant mother come in who we know everything except whether there's going to be a low birth weight, and we want to predict the risk because maybe we can do, some extra things to help avoid a low birth weight, like maybe giving some nutrition training, some guidance, some help, support, etc. And so that's really key to really what we're doing with predictive modeling. So let's step out here for a minute. And I'm going to go into RStudio. As I mentioned, you can see there's all kinds of stuff here we can do in RStudio. I'm not going to focus on using RStudio, but I do have other videos that cover that. And what I'm going to do is just highlight parts of what I'm running at a time. So that's highlighting 2 lines. And if I click the run command, it will just run these 2 lines. And I'm going to clear out the bottom console so we can see things as we run. Output's going to come out down here. Okay. So I'm going to run this, and you can see we brought these in. Now, what are these? These are libraries. These are packages that I'm bringing in, which are just functions that I can use. Without them, I don't have availability of certain functions. So the library mass actually gives me the data set, I believe it is, as well as some extra functions. And R part gives me some extra functions I can use as well. And you can see in the script, which is available on the GitHub account, where I got some of this, so you're welcome to go in and take that. I borrow bits and pieces from people, and I always like to credit them, so there's links in there, etc. But this particular case, the birth weight data set is already built in. So if I just highlight that and do run, you can see I can display the data set. Now, to get help on what it is, this is why it's nice when you get data in packages like this. I can do help, and it gives me some help over here. Can't really see it, but you can see help, and it tells us what all the different columns in the data set are, so we can get more information. Nice little command you can use at str, which gives us the structure of a data frame. So you can see, so this again is a built-in data frame. It's part of the package, which is kind of nice, and I don't have to like do extra work. And so you can see here too, if we look at the data frame below, we can see most of these things are integers, right? So that's what's going in to drive what we're doing. The head statement can be useful if you just want to see a few rows of data. You can do that. And nice thing again, a very common part of when we're doing any kind of predictive modeling, typically we do a lot of analysis. We try to look at the data. Do we have a lot of nulls? Do we have missing values? Do we have enough to work with? But I'm just trying to get the concept across here, so I'm kind of skipping over a lot. But one thing I might do is a histogram. And you can see here, if I zoom in, get a histogram of birth weight, so I kind of see a distribution. And it's somewhat normalized, I guess. It kind of looks normal. Another useful statement is I can do this table statement. And what it does is it shows me, I'm looking on the low column, the frequency of each. So I can see that out of this birth weights, 130 were not low birth weights, but 59 were in the data set. And that tells me also I have 189 rows or observations. Now the attach command is kind of handy because without the attach, I would have to keep specifying the data frame involved. When I do an attached function, it means that it's going to assume that that's the data set you're referring to when you refer to column names. So I'm making my life a little easier here by doing the attach. Then what I'm going to be doing is doing a subset, as you can see here. I'm selecting and I'm picking out two columns, age and the LWT column, which I think is the mother's weight in kilograms. And then I'm just going to do a box plot just to kind of demonstrate how I might use, for instance, a box plot. Box plots are really nice because they give you a sense of the range of values, and it breaks it into quartiles, which are fourths of the values. And the circles above and below tend to show you like outliers, things that don't fall into the normal distribution. What you do with outliers is always up to debate, so I'm not going to even get into it here. But all right, now I want to use this library called Psych. Now, if you want to install any of the libraries, you can always go up to Tools, Install Packages, and if I want, for instance, to install Psych, I can just go in here, and you can see I could just say Psych install, or you can just use the Install Packages command, which is all it's going to do is generate that. So I'm going to bring in the library, and I'm going to say Pairs Panels. And what I really love this particular diagram because it's a great way to get a correlation matrix, basically. How did things fall out in terms of the linear relationships? Now, it's not the best data set, to be honest, for doing linear relationships because ideally what you want to see is dots that sort of form a shape. It's almost like a line going up, but the dot's not perfect, but they kind of form a pattern, like maybe going up or down, and you can draw a line through them as we saw in the earlier diagram. If we look at this, we don't see many patterns like that. Closest might be, I think, age to weight. You got a little bit of that, but it's pretty scattered. So again, drawing that line is tricky. But what we can see here is, like, if I look at age and the LWT, there's only a 0.18 correlation there. So not really strong. This one is kind of weird because these are categories, race versus smoking. So probably not a very useful metric. So not getting a huge amount of help here, but still a very cool looking diagram. If we saw strong correlations, then it's kind of more encouraging. But what we typically do is combine several columns that we're going to look at doing, bring a few columns together, and see if using them together, it provides more of a relationship that we can predict. If we saw something that did create a nice line, then we have a linear relationship, and we might be able to use what's called a linear model, which focuses on that kind of relationship. So another thing in doing this kind of predictive modeling is when we bring data into the model, typically we need to convert it into what's called a factor in R or some sort of categorical variable. If you do brush up on your statistics, you haven't, when you're going to be doing probability analysis, you really have to create kind of bins. Like let's say we want to sort out things that are going to be something like, we'll say people who are going to come into buy insurance, and we want to say if they're high, medium, or low risk. Well, we've got 3 different bins, right? So we might have 0, 1, 2 as the bins we're going to put them into, and they have to be numbers when you're doing predictive modeling, this kind of statistics. But we also like the idea of having a description associated with it. So what we can do is use what's called a factor. And what we can do with factors is it still keeps the textual name with it, but it's behind the scenes, it's really a number. So I think of it a little like code tables from my SQL background. I might have something like MasterCard, Discovery, Visa as a code table, and then it's actually an integer in a key column or something like a lookup value, and the number is also there along with the description. And that's kind of what factors are. So behind the scenes, the takeaway is it's got to work with numbers, so we convert these into categorical variables. And that's true no matter what you use, but in R they call them factors. In Python, use one hot encoding, and they use a different, they don't usually call it factors, but that's what you're doing. You're just creating these bins for your statistics. So here we've got the seek stands for combine, and I'm passing in a vector, essentially a set of strings, which are going to be the column names that I want to pull out. So let me just run this so I can get that. And so it's just storing, it's kind of over here, it's just storing that list of values. Let me just highlight that so you can see what that looks like. So you can see it's just stored that value list. What I'm going to do now, though, is say I'm going to use the birth weight data set, and I'm going to subset the columns, and I'm going to use this lapply. And what I'm doing is basically cycling over the columns and converting them to a factor so that it can do the predictive modeling on it. So again, I need to do that because if I just try to pass in the numbers, it won't be able to convert them into categorical variables. So here I want to do that. I'm going to turn them into factors. Now we've done that. What I want to do is I need to set my seed. What I need to do now is to break up my data set. Remember before we talked about the fact that I need my training set, which is going to be used to build my model, and then I need a test set, which is going to be used to see if it's working or not. So I'm going to say set seed is because I'm going to be using a sort of random calculation thing, do random sampling, and so I need to set a seed ahead of time. Now, oddly, you might think that's going to keep changing every time, but generally you don't. You kind of want to predict the same, use the same set over and over again so that you get the same results. So you set the seed 1, you're going to get the same extracted set, etc. And that makes sense because you don't want to have this thing constantly shifting around on you. So I'm going to say sample, and this is going to get 70.75. So in this case, I'm just doing 75 instead of 80%. I'm doing 75. I'm going to be multiplying that by n rows. So it tells me there's 189 rows here. So what I'm really doing, and it's easy to show you, so I'm going to run these 2 lines of code and then I'll walk through it. If I look at train, you might think I've got a subset of the training data, but I actually don't. What I have is a bunch of indexes. Because what I did was I used the sample and I said 1 to n row, right? So that's 1 to 189. Give me back only 75% of the numbers. So it's basically, it's just randomly giving me back from 1 to 189, 75% of those numbers. And that's now a list of indexes I can use to pull out of the data frame and therefore create my training set. Now, a little trick in R is if I see this birth weight, right? This is all my data. If I wanted to get all the data except the list that's in here in this training list of numbers, I can use that as my first column, which identifies the rows of a data frame. And if I leave this blank, it means all columns. So what I can do here is I can say I just want to get all the rows in my data frame that are not indexed by this, that are not this row number. So let me show you what I mean. I've already done this, I think, but I'll do it again. And now, if I look at my test set, you can see that's what I've got in my test set. It's a subset. So what did I basically get? I got a test set that is everything that is not in my train set. And my training set is really just integers now, but I'll show you how I'll use that in a minute. So I'm going to start building the model. So I'm going to bring in the library rpart. That's why I'm going to use the rpart function to build my model. And I'm going to be storing my model result as essentially an object in the birth weight tree name here. What I'm trying to predict is low birth weight. And this is sort of like saying using. So what am I using? All columns is the period, but not the birth weight. Because I mentioned the birth weight by definition is that. If I know that, I already know if I have a low birth weight. So why it's there exactly, I'm not sure. But you might have something like that in historical data, right? You might have a column in your historical data that is essentially equivalent to what you're trying to predict. So you might have some redundancy in terms of values. Like you want to know the Boolean part, not the actual birth weight. So here we're passing in the data. And we're passing in the birth weight data. And notice now I'm passing in the training index list. So I'm subscripting basically. I'm saying give me all the rows that were in that list of numbers I pulled out earlier. And the method I'm using is classification class. So let me run this. And I've created a model. You can see this is tracking over here all the models. And I can highlight it. You'll have different information, statistical information, etc. It's telling me what it's doing. And what you can see is it's a decision tree actually because of the different greater thans. So we can plot this. Let me plot it. And you get a little picture of the decision tree. So you can see it's coming in and doing a decision and then branching. Now, a nice thing with R is there's lots of packages out there, and some create prettier graphics than others, and some do cooler things than others. I'm going to use the Rattle package because it creates a very cool looking diagram, much better looking. And we can see this. So we can now get a better picture, okay, of the birth weight comes in. And so you're saying LWT greater than or equal to 106, yes on the left, no on the right. And it just keeps going down this branch. Now, it's a horrible predicting model, to be honest. It's not doing a really good job, as we'll see. But I love this one because if you're used to programming, if you come from the background, this sort of if-then-else logic makes a lot of sense. And this particular model follows that kind of logic. Most models do not. And most models are not very easy to diagram either. So it's another reason I like this one. All right. And we can do this summary function, which will give us some information about the birth weight tree. So we get all kinds of cool information. But that's not really the focal point here. Now what I want to do is try to use that model to predict things. So here's my birth weight tree model. Now, remember the test data set? You can see it there. So now I'm going to pass in the test data set. I'm telling it this is the classification decision tree we're using. I'm using the predict function, passing in my model, and the results are going to go in here. Okay, that's going to store all the results. Now, just to show you, it's basically got all those indexes, but it's saying a 0 means it's not a low birth weight, and a 1 means it is. So we get a sense of that. So now comes the fun part. Scoring it. How did we do? Is this a good model? Evaluating the model. So we're going to use this library function called gmodels and this cross table, and then I'll explain it. It'll be a lot more intuitive to see what's going on. Okay. So what we have here is we have in this, again, the test set. So in our test set, we have a total of 48 observations or rows coming in. Of them, 31 are false. And we've predicted 24 were false, but 7 were true. So we've got 7 which were incorrectly predicting a positive, that it was a low birth weight. Now in the next one, the low below, how many actually had low birth weights? Well, in this case, 17 had low birth weights. We predicted 10 would have low birth weights, so we matched up on that, but 7 we misclassified. So we go down here and we can see not the best outcome, right? We missed some biggies. This is kind of a pretty off prediction. So get an idea there of that's one set of predictions. Let's try, and this is a very common practice in machine learning predictive modeling. You try one model, you see how it does, try several others, sometimes many others, and you may find a model that works better for certain types of use cases and data than others, and that's what we're going to do next. So we're going to bring in this library called class. I'm going to break up, this is actually extracting just the results into the labels, which is the outcome. So you can see training labels, just giving you the actual raw numbers of true false. I'm going to be extracting new data, and I'm pulling out some columns, some data set. And I'm just pulling out these columns. And I'm going to be using what's called the KNN. It's called the nearest neighbor. And this is a classification model in which it looks for characteristics and it kind of groups them together and says the thing that's the closest to what the new instance coming in is what I'll assign it a value. Now KNN is a little strange in that it doesn't actually, we're going to be passing in our training data, but we're also going to be passing in our test data at the same time. And so it's a little bit different in that way. We'll create this here. And it's one of the odd things. So you don't actually save. In most cases with models, you save it and you've got an object called the model, and then you can reuse it. KNN, you train and use it at the same time. So it's a little bit odd in that way, but it works out well for evaluation purposes, because as we go in here, I'm doing that, picking the wrong expansion, we can see that now we have 31 that were false, and we picked 31. We found 17 were true, and we picked 17. So we get a perfect score. You really probably shouldn't get a perfect score, and some people would say if you get a perfect score on your data, you probably did something called overfitting. But for our purposes here, we can see that in general, this looks like it's doing a better job than the other model, and so we might choose this to do our predictions. Now again, this one's a little odd because typically we'd store that model and we could reuse it, but the KNN doesn't really let us do that. All right, so that gives us kind of a sense of creating the model. We split the data, we put a training side through, and the training side builds that statistical correlation. It's as if we went through and based on all the values, we went on a pen and paper and calculated the probability matrix, whatever we're using, and said, okay, now I know how to do this. And then we pull in new data and actually try it. So the typical thing you would do once you've trained your model is you would store it somewhere, and then new data that's coming in, say readmission, so new patients are being admitted to the hospital, or even pre-admissions, you could have it go and hit this model, and based on the patient information say, this person's likely to get readmitted. So, you know, be careful. If you're admitting them, be careful because you might end up sending them home too early. So it might be good for something in an emergency room to kind of evaluate new patients. So we saw some of this. I'm kind of put some slides in here, but we can see we separate. And if it's a little confusing in the code, that's really not the point. So don't get bogged down. Don't worry. The important concept is you separate out training data, which is used to build your model. You hold back a little bit to score the data. It's kind of like giving the cheat sheet that you can use to see did the model actually work. And the key thing about the test data is you don't give the model the answer. You use it to actually as if it's brand new data and the model doesn't know. We start using a decision tree like this. And I like this visual because one of the challenges with machine learning is it can be very difficult, especially with the more complex models, to explain what's going on. How is your model working? What is it doing? And this can be a real blocker for some people who like to be able to explain everything. In the case of models, sometimes you don't really have a good visual that you can use like this. In fact, most times you don't. In deep learning, neural networks and things like that, they're getting to be, unfortunately to some people, more and more black boxes. And you have to look at statistical numbers outside of it to try to get your best gauge on, how accurate they are and why they work. And so that's one of the challenges. The key thing you have to look at is using some of those metrics around it for evaluating, retraining and testing them again. Always watch the models. Don't just create them and throw them aside and say they're good for the next 20 years. You got to keep reworking them and making sure they're working correctly. And we saw here this confusion matrix where we actually compare the results. What was the reality versus what we predicted? So again, the process: analyze, clean the data, determine the columns that predict the answer, select a model to use, train your model, evaluate the model's effectiveness, and use the model. Most people get hung up on a couple of steps here, and ironically, it's not the most challenging step. The most challenging step is step one. If you're like me, I've worked in ETL and data warehousing and BI for years, and so to me, that's like, oh, it's easy, clean, sort, whatever. If you have those skills, take heart. You're in high demand. This is a really needed area, data wrangling, they call it. Really important for this. So if that's an area you're skilled in, great, you're going to need it. SSIS could very easily be the thing you use to kind of do that if you want, but typically people use Python, R, or SQL to kind of get through that step of cleansing the data. Now, bear in mind, you may have to pull data in from a lot of sources, but that's actually up to 80% of the work in data science. And that's things I've heard from Microsoft presenters and other presenters on data science, that cleaning and analyzing and data prep work can be by far the most, really the most difficult step. The next one is determining the columns to go into the answer. And typically domain experts and data scientists can help with that. And there's ways of doing that. So I think most people have a little more intuitive sense around that. The next one is really a point of confusion for a lot of people. I'll try to talk a little bit about it, which is selecting what model do I use. There's a lot of models out there and you'll start to get like lost, right? It's like trying to pick a new car. There's so many models and so many variable options I can use. I'll talk a little about that, but don't get too bogged down because there's ways to consider that, again, kind of an exploration. It's not meant to be I just make a snap decision. You explore, there's options. You don't necessarily, you want the best, but it doesn't mean that everything has to be perfect right off the bat. It's a growing process and there are people that can help and lots of stuff out there. Okay, and I think we did talk about evaluating the effectiveness of a model and things. So we'll talk a little more about these things, but that's the general steps. So revisiting this discussion about driving into Boston, I do want to revisit a few things that kind of get back to model selection and things we need to bear in mind. First of all, we're looking at this. We're going to, again, what type of outcome are we looking for? So when we talk about what model type to predict, remember I said we looked at classification models because in the case of low birth weight, we're looking for a true false. So there's a number of models that can give an outcome prediction of true false, and many of those can also give you true false, or it could be 1, 2, 3 and types of options like that, like maybe risk of an insured high, medium, low. That would typically be classification, or what species is a plant, that kind of thing. So that different models can do different things. Some people are trying to predict sales. I want to actually predict my sales amount in different points in time, so that's a continuous variable. So you do need to consider whether it's a continuous variable or not in terms of like what models you're choosing and how you proceed. Again, the output columns, how many output columns you have, input columns, can be really critical. You can have hundreds, you can have thousands of input columns, and you start to need more and more computation speed and memory and things like that when you start to train your models with more columns. And a little takeaway to really bear in mind, because it's easy to overlook, training the models is the part that's heavy computation. It can take a long time, etc. But once the model has been created, it's pretty much a lightweight program at that point that doesn't take a lot of resources to actually bring in new data to score. So in other words, if I'm trying to train a readmission model that says whether or not somebody will be readmitted, that could be a lot of work. But once it's done, to have new patients come in and just hit it against that model to say, is this patient likely to be readmitted? That's very fast. So you can often shift, and a big trend happening now is train your model in a heavy-duty environment and then move your model somewhere else to actually use it. So anyway, number of input columns can be different. Some models in R, for instance, will support only a certain number of columns, and when you go above that, you actually have to change models and things. So there's a lot. Can be a key feature. How widely do the outcomes vary? I mentioned that, so you do have to consider that. If it's really all over the map, it can be really difficult to build a good predictive model around it. And how much input data do we want to use? Again, this gets into a little reality check, but I do this simple model, and sometimes people get the idea that this is magic, and that I can just have, for instance, in this case, 158 rows of data and like 8 columns, and I can do anything in this prediction. So it's a nice demo. But would this really be enough to do a true predictive model? I don't think so. I think in most cases, you're going to want millions of rows if possible. And generally, as much data as you can get, the better in terms of reflecting it. And you want to make sure the data reflects what data you're scoring. So if you're scoring, sales in the Boston area, well, to make sure you're using data on sales from the Boston area, not data from LA or something like that. Because if you're looking at disparate data, they're very different, then the predictions won't be reliable. So you have to make sure you're sampling, however you're getting the data, that it reflects the type of data you're going to be using to score as well. So you want to make sure you're doing that. So the takeaway there is the complexity and the volume and things can be a lot more. This is a simple example, but it's not magic. And that's the slide. It's not magic. A lot more data is typically used in model training. You may use a lot more features. Sometimes you have to actually put the features themselves through a predictive model to do weighting and things like that and actually map them out. So you can actually have a sort of multi-layered modeling. And many times you may want to, for instance, I worked on one project where you give the model a whole bunch of columns, like 300 columns, and then it goes through permutations and iterations over it, and it will tell you which features it thinks are good ones to use to get the best model. So you're actually letting AI predict what you should be doing there, which is interesting. That's called dynamic feature selection, but you wouldn't normally think of that. So, but that's very resource intensive to do that. So again, you have to think of these things. Data quality and completeness is really key as well. If you have missing data you need to figure out your outcome, you may have to go back and get it, or you may have to stop recording information that you didn't think you needed, but now you do to predict an outcome. And I've seen that on like web analytics. You want to track a certain thing, and you find out the weblog does not store the key piece of information you need, and now you have to go back and start adding it to your weblogs. Hopefully, you have the data you need. Do you have a lot of nulls? Do people who are supposed to input the data get away with skipping it, and now you have null values? Is it possible that some people who are supposed to enter a number or amount just enter 99, and so you end up with a lot of bogus values? Those things can really put a challenge in for machine learning. So data wrangling, the transformation, can be significant, and don't underestimate it. So my point and the takeaway in this, as this comes from truly a sales position at Microsoft, is that it's not magic. There's huge value to be done, and sometimes you do have some nice use cases, low-hanging fruit, they call it, where you can get some good value and pretty easily. You got the data pretty ready to go. It looks good. But machine learning and data science, etc., is really the beginning of a journey. Just like you started maybe years ago building business intelligence data warehousing, you didn't think you just flip a switch and it would be there. And machine learning and data science is a journey. It's very rewarding. It has a lot of value. And I think it's important to understand that the journey itself can yield many benefits and business value besides just the models themselves. And so look at it that way, and I think you'll be a lot better off. The worst thing you can do is go into it and think it's going to be magic, because then you'll be a little disappointed. It's not magic. Now, choosing the model can be challenging to people, and I like this slide. You can go to the link there, and this is Microsoft's Azure cheat sheet, or algorithm cheat sheet. And it's got kind of a little branching here, and you can figure out what makes sense. Do you want classification model, clustering model, anomaly detection, all these different things. So this isn't a bad place to start. There are many, many different types of models. My best advice would be figure out what you're trying to do, and figure out if there's similar models, or maybe there's examples out there that can help you right off the bat. For instance, I was talking about getting into Boston at a certain time. How do I get into Boston? How long will it take? Well, really, if you think about it, traveling into a given city and the amount of time it'll take is pretty similar to sales forecasting, especially if you look at it on a daily basis. I would guess that all the factors that went into how long it will take to get into Boston would also go into something like how good will a given store's sales be on a given day. If you're Dunkin' Donuts and you're trying to figure out how much your sales will be, I'm guessing that weekdays, Monday in particular, early in the morning, you're going to have heavy sales. Later in the day, it's going to taper off. Maybe middle of the day, you get some business again. Probably tapers off a lot at night. But then you might have, groups that meet at night and get sales there. Weekends probably get pretty good sales for a while. It depends on time of day. So different things like that. But you can imagine that one type of modeling, which uses continuous variable as your output, that outcome, can also be used in another case. So think about the type of modeling in situations, and if it's similar, you can probably use the model in a different, specific scenario. Also, just go to Bing or Google and just search, sales forecasting, patient risk, etc. There are a lot of different examples and code and things you can cut and paste and play with and see what works for you. Finally, you have options. I'm teaching you the concepts here of machine learning and creating a predictive model, but there are different ways to approach this. So I'm taking this part of my discussion is really targeted at business managers, business leaders, IT directors, CEOs, CIOs, people who are trying to, from a business marketing directors, people are trying to look at this from a business value. How do I approach this? How do I start? Well, I'm talking about it from a build it yourself, DIY, because I'm a consultant. It's what I do. I like all the tools. I'm a big proponent for Azure Databricks. And so I do focus a lot from that standpoint, but it's not the only option, and I'd be remiss if I didn't say so. First of all, you can use pre-trained models to do a lot of types of machine learning for you. And Microsoft has something called cognitive services. They're already written. They're trained. You don't have to do any of that work. You can just take it and make a call from various places using like a REST API call and just say, what person's face is this? Or what is this in this picture? Or translating languages. We'll see a bunch of different things you can do. And the pre-trained models will just give you that. It's a service. And you pay as you go. Just score this, essentially. So that's a good example. And it's not a bad way to get familiar with machine learning because you're not building yourself, but you're getting familiar with how it works and what it does. There's also ready-to-use solutions. So Microsoft has a massive network of partners, all kinds of companies and things that have built their home in Azure and do a lot of work with these tools. And Microsoft works very closely with them to get customers maximum value and get them up and running with complete solutions as soon as possible. So if you don't want to build it yourself, but you want the complete solution as soon as you can get it, that may be a good option, ready-to-use solutions. Use the cloud. Azure is a great resource. What I find is I don't like to spend a lot of time configuring hardware, worrying about setting properties, creating, if I'm trying to scale on a big data platform, creating my cluster, worrying about how many machines I have, do they have enough memory, all these different problems. I want to jump in and work. Use the cloud because the cloud was designed to let you scale, to let you pay as you go, and you can just delete it when you're done if you don't want it. It's much harder to do that kind of thing on an on-premise environment where people are ordering hardware and then a week later you say, I don't want it. And you're like, well, we've just ordered all this. Whereas in the cloud, you can just create it, delete it, and you don't have to pay for it, except for what you use. And get help. Lots of help available. There's all kinds of YouTube videos like this. There's a lot of training stuff. But I also mean, consider bringing in partners, consulting companies. Microsoft, again, has a lot of consulting partners we bring in. And we select them based on their ability to help you with what you're trying to do. So it might be a partner that's really good in deep learning. And maybe they've also done, say they're using Databricks. So we bring someone who really knows Databricks. Or we bring someone who knows ML services on Azure. So we try to match that up. But getting help is really important. If you're new to this, you're in a company, you're trying to get this going in your business, it's a good idea to bring in experts, people who can help you. I don't do legal stuff. I always go to lawyers. I don't try to do my own heart surgery. Not a good idea. And in the same way, if you're not sure what you're doing in machine learning, there's nothing wrong with going out and getting help. But I would advise, learn as you're doing this. Get help, but also learn and get the consulting company or whatever to train you as you also go. So as promised, this is just a sample, and it's a little bit outdated, but it shows a sampling of the kind of cognitive services, pre-trained models you can do. So Face API will do things like recognize faces and things for security, and you've probably seen that. My Surface does that, translating speech. So one way to kind of play with some of these is there's some apps you can go for, like on my iPhone. I downloaded Microsoft Translate, which is actually kind of handy because you can speak into it. It takes what you say, translates it into text, but then it will also speak it in an alternate language. So you could be in another country and use that as a sort of universal translator. I'm actually surprised because it supports Klingon, which is really important. If you get stuck on the Kronos, the Klingon homeworld, you will have a translator. Unfortunately, it doesn't speak it, but at least you'll get it in text, which is good because Klingons are not very pleasant. Anyway, you also get the speech API for Bing and language understanding, text analytics. There's all kinds of good stuff in here. It's a fun place to play. Go to the website because there's a lot of cut and paste code, and you can just paste Python or R code or whatever into your editor and start seeing how it works. And it's a good way to kind of say, oh, okay, because you're kind of looking at the user side of the model, consuming a model as opposed to training it, which can be a lot of fun too. Finally, I would be remiss if I didn't give you some resources where you can go. My favorite one for learning machine learning, especially with R, is this Machine Learning with R book. I had the second edition by Brett Lance. Really like it. The author goes through a lot of nice explanations and examples, and he kind of goes through different types of models. And I love his explanations because they really make sense. You say, oh, okay, I get it. That's why you would use this. That's how that works. If you're new to R, The Art of R Programming is a great book. It takes a really nice sort of slow build up and really gives you a sense of how R works in the language. You also have R for Everyone book there, which is good. Learning R. And if you're learning statistics for the first time, to me, statistics, as riveting as it can also be a little tedious, to be honest. And so I wanted a book that was going to be kind of fun to learn it, that didn't take it like it's, it's drudgery. So I like this book, Head First Statistics, because it's kind of like cartoons in there, and they say Mary's trying to solve a problem, and it made it more relatable. So I found that to be a good book. And there's a lot of stuff out there on statistics and stuff. You don't need to do data science and machine learning. You don't have to be a PhD in statistics, but you do need to understand some basic concepts, central tendencies and p-values and all these things you're going to hear. It's good to know what the terms are and how you can use them in your machine learning. So wrapping up, we did a brief introduction to the R language, which I hope was helpful. And again, go to my other videos or other places and you can find a lot more, or use the books I just mentioned. All this again is available on GitHub, so github.com/bkafiki/shared. And also we discussed what a predictive model is, and we've learned that it's just something where we use historical data to try to predict the future of something. So we use historical data maybe on patients to predict the likelihood of readmission. We look at historical financial data. Maybe we look at payment history data on different customers to determine the likelihood of default, fraudulent transactions, etc. We kind of look at history, though, again, trying to get to the future. We walk through doing training a predictive model and then evaluating it. And I gave you some cautions, recommendations. And as much as I would love to say it's just magic and it just works and it's all rainbows and unicorns, not quite like that. It is great, it's fun, and it's not difficult per se, but it's like anything. It's a discipline and it has different facets, and it does take time to really get good with it. Hope you've enjoyed this. Please subscribe, share, and until we meet again, thank you.